We'll start session. Actually, this is a cover-up session, and this is a quick review that you needs to learn, like theoretical part for the most part. Most of the time, we are planning to discuss today theory rather than the practical scenarios. So probably you have learned a very good practicals from Mr. Nadira. So, so almost you are ready to apply for performance modeling engineer or performance engineer or automation QA engineer kind of job role. But theoretically, you should have some understanding to complete this subject. So those parts mainly, I think Dr. Menaka started a bit of these things, but I believe it's incomplete, and I'm planning to like give a very high level, quick brush up for you. If this is the very first time that you are learning, to be honest, it might be a big theory component comes to your head. Probably it might be really hard to grasp all of these things within these 2 hours. But if you have some theoretical like going through, then this is a good session to get a quick brush up for to get quick overview regarding the subject. So first we will start the topic capacity planning. This capacity planning is a very important process, especially once it comes to manufacturing, different kinds of service industries, or especially once it comes to information technology. We have call centers, and we have different kinds of networking models that needs to plan. Nowadays, once it comes to this cloud computing, we have capacity planning. Cloud engineers needs to perform nice capacity planning before we start the month, because we have to bill it. So overall, this capacity planning is a very large vector, but we are focusing on bit of theoretical aspects related to this capacity planning. Mainly, we have two aspects under this capacity planning. One is demand forecasting. The other one is capacity requirements. Once it comes to demand forecasting, we have different kinds of quantitative methods, and we have different kinds of qualitative methods too, because we want to forecast how much of the things are required in future in very general terms. Qualitative and quantitative means a bit of complicated story, because whenever we have this data or we have numerical values, we can give a, like we can predict the value in future. For an example, if we take a situation like a cloud computing engineer, we have used this much of storage last 3 years per month, this much of storage, this much of storage in this hour. So we can forecast upcoming storage requirements, or else network usage, how the bandwidth consumptions are. So if we have data previously, 1 month, 1 year, or whatever the time that if we have, then we can smoothly continue the process without any problem, right? Predict when, sorry, how much of the spaces or how much of the network bandwidth required for next hour or next month or next day, or something that we want. The other hand, we have qualitative methods, especially it's something not based on a numerical value, but it's based on some experience, some experts options, right? So many other things. We have some qualitative factors, especially the people who worked in that domain for years. They can easily interpret, they can simply say, all right, this much of uh, data we require. If you take very simple example, a shop nearby your house or a city or somewhere, like a seller, simply the business owner would say, all right, we want this much of things tomorrow. If it is like, for an example, think bread, right? If it is a bakery, number of bread, they know tomorrow this much of breads needs to sell, like prepare. It might be plus or minus some value, but mostly they can. That's based on these qualitative methods. They have this intuitive skills to get all of these things quickly. Somehow this is one aspect of demand forecasting, qualitative and quantitative. The other key aspect is capacity requirements. We have to plan the capacities short term as well as the long term. Short terms means we have very limited time. For an example, 24 hours, 1 week or something. Long terms means we have to like invest, or we have to plan for a long term. Now, for an example, if we have an organization, if we are planning to create, or if we plan to design a shop or an organization or something, if we have a capacity plan, the number of people who work under this organization, how much will be. Nowadays, if it is information technology companies, I believe almost nearly 90% organizations working from home. Very rare we can find like come physically and do these classes, to do this work, because this is software engineering is not something that we need to uh, work in an organization, in a place, right? So the big heads, the knowledgeable people in the industry especially, they are always nicely planning, because every space is a cost. If we rent a building, it attached to a cost. So they want to minimum space, but they want to run business smoothly. So what they are doing is they are giving working from opportunities. It's worth for both sides. The organization wise, they save a lot of cost, because electricity, water, space, and everything is like nothing. So because that pushes to the worker side, it's a big advantage. The traveling time, the time that we spend for the preparation, all these things, the tiredness, all of these things are removed. So in both hands, it's work. So the capacity planning, if it is an information technology company or IT company, you can have a virtual environment. You should understand this clearly. In the other hand, if it is manufacturing company, we'll get an example. If it is a factory that making toys or something, so they want to have these machines and stuff. The workers should physically appear in that place, and they should do it properly. Toys or clothes or something like garment factories, like, so all of these things they should prepare well, because it's really important. They can't do it virtually. It's a must to have. But there might be some third party organizations and stuff, like smaller components, they are uh, reducing the workload to somewhere else. So altogether, you should understand the capacity requirements focuses on these things. So whenever we are planning this demand forecasting or capacity requirements, we should understand whether it's a short term or a long term, what kind of strategy that we can go. So it's obviously focused on this proper optimization of all of these performances, so the capacity planning in our work. Next, we have different kinds of capacity planning types. We have one is lead strategy, then lag strategy, and match strategy. What we have is lead strategy, adding capacity in anticipated of demand increases. So what we have to do is we have to add the capacity in an anticipation of demand. Future we have, so we will generate in future this much of. Lag strategy means adding capacity only after demand has increased. Now, if the demand is increased, then we are increasing our uh, whatever the resources. Right? Now, for an example, think if we are using cloud resources, then we have to go to this both the lead strategy and the lag strategy. For an example, we are planning, or we are adding the capacity anticipated value next day, tomorrow. The number of network users might be this much. So we can go for lead strategy easily. In the other hand, the cloud resources are giving nice opportunity for us to have these lag strategies. That means in case sudden um, user requirement is going on, so we can expand for next couple of hours even. So you can easily articulate with the short-term planning and the lag strategy. So we can find, like, if it is lag strategy, then it's for the short term, mostly like after the demand is increased. So people are increasing, so we have to keep much more space. So that's the story. The other one is match strategy, adjusting capacity in small increments in response to the change in demand. Some of the things, right? Some of the things are changing like day and night. For an example, think the network. So they have the high demand in 8 to 5. Then after midnight, 12 p.m. to 6 p.m. or 6 a.m. or 7 a.m. We don't have much more users. So network bandwidth is almost free. So this match strategy gives opportunity like very low cost, you come and enjoy, or sometimes free. So that's kind of a capacity planning, right? So these are three types of capacity planning. If you go to literature, you might find much more latest and much more stronger capacity planning methodologies too. But in general, you should understand these capacity plannings. Some tools and techniques related to this story of capacity planning. First one is capacity utilization. Then we have capacity fusion. Then we have bottleneck analysis. We have queen theory. What kind of story that related to this capacity utilization? Right? The ratio of actual in output to the potential input. It's potential input theory. Understand? This is a nice technique to understand the demand, or to go for a long lag strategy, or whatever the strategy that fit for the case, because we want to find out the capacity that focus on the utilization, or how much we want to work on, right? The other point is capacity fusion, which is extra capacity to handle sudden increases in demand. Now, if you go to the previous slide, you can see lag strategy focus on adding capacity only after the demand has increased. So if we have this technique nicely applied, capacity fusion, then you can easily tell this kind of demand we have, a sudden increase we have. Other two are basically nice two more techniques that we should detail go through. These are very easy techniques anyone can understand because it's based on some of the data we have. In the other hand, we have bottleneck analysis and we have twin theory. So what is this? Bottleneck analysis identify the addresses of the limitations of factors in production process. It's not just the production process. It might be even in a web blog. By reading a web blog, we can find what are the web pages that not performing well, what are the hitches we have, where the performances are lagging. Sometimes it might be the reason behind the front-end framework that we have used, or else incompatibilities of these products. So if you learn a bit detail later on, you might learn especially once it comes to data science and other concepts, you might learn process mining, process logs, event logs, and many other things. Then we can perform a nice bottleneck analysis. I'm not focusing on that this stage, but definitely if you are planning to go future a big detail learning, definitely this bottleneck analysis is a big story for a business. In every business, where the processes are lagging, where the processes are not working very well. Fourth part is the biggest story. For the most, like nearly 80% of the time we are spending to understand this queue theory. Analyzing the wait times and the queue lengths in a service industries. Again, it's not just service industries, it's going more towards nowadays to the technical organizations, especially like the network ingestion, so network slowness analysis, right? So if the data packets are in a queue. Now, this is nothing just like probably everyone stayed in a queue because many scenarios we have the service provider in here. This is the bird's eye view. This is the service provider, and we have people in here. For an example, think a bank. So you are in here, right? And another customer is in here. You are another customer in here. Even if you go to a supermarket, even if you go for a bank, right? Petrol sheds everywhere, right? Everywhere we have queues. Now this queue is something that we should maintain nicely, because if this person is getting hours to reach to the head or the top of this place or the service provider's place, this person might lose, like remove from the queue. That means we lose a valuable entity from our business. Sometimes this might be a billionaire, right? So we have to maintain this queue nicely, right? We have to maintain this queue nicely. What are the strategies? What are the techniques? What are the tools that we can use to successful queue, right? Because if it is no queue, zero queue means this service provider or the person who is in there, mostly will take the service provider, is idle. So nothing to do, free, right? A business do not need to entertain anyone free. They needs to get a work done. So every second there should be some work. So there should be a queue, at least one or two people, there should be a queue. Sometimes if you go to a big like retail chains, or sometimes like for example the businesses we have, you might see the cashiers, number of cashiers are changing based on the time. Evening, 4 5 6, most probably the queues are filled, like they have all the people coming to purchase something, and so on and so forth. And in the other hand, all the cashiers are busy at that time. If you can remember, the same organization, same business location, right? If you go to like go around 12 1, like 10 a.m 11 a.m, mostly the people are less, so the queues are less. So what the organization, the managers are doing, they are taking the people who are in the cashier, taking out and get some work done. Mostly there might be one or two maximum cashiers are there. I'm correct, right? So this is based on like how they plan the capacity, they how they do all of these stories nicely. And the other hand, if you can remember, some of the cues they are telling here, we have this much of length. If we have length or the number of people more than this line, we'll open another counter for you. I don't know whether you have this experience or not. Probably you should have. Many businesses doing this, because to make the customers entertain. Because when the length is extremely high, definitely people will remove from this queue, because we are working with different kinds of humans, different psychologies, different attitudes, and so on and so forth. Right? So that's the story, right? So it's a big story that we have to understand how to manage this one. It's not something like you can take, like intuitively you can think, all right, go for this and that and this. But if it is a scientific way, there is a much more nice story behind this management. Let me stop this slide with a nice introduction. Now, you know, guys, I think most of you feel we have number of queues, right? We'll take the simplest example, cashiers. We have cashier 1, cashier 2, cashier 3, cashier 4, and so on and so forth, right? We have 4 cashiers in this place, right? Cashiers, all of these cashiers we have, and we have people in here, people 1 2 3 4 5, and so on and so forth, right? So the people are going through this queue, and each queue do have different kinds of people, different number of people. This is the standard method, or many places that you have used, you have seen this method. But the real story, this is not the best approach. That means dividing these cashiers into different kinds of queues is not the best approach. The best approach is we have only one single queue, right? We have only one single queue. Then all the peoples are going through this queue, right? All the people are going through this queue, and we have number of cashiers in here. So each cashier takes the next one. Sometimes you have seen this in some banks. This is the best approach. The reason behind is, in case if one cashier lagged, right? If a big something is going on, then the next other 3 can continue the process, isn't it? So this one is lagged, no worries at all. So the next one is goes to here, next one goes to here, next one goes to here. Again, the next one goes to here, next one goes to, like, after a couple of people, only this person is going out. Then after, the next person is coming happily, because no problem at all. We'll get the same scenario in this scenario. In this case, what happens, guys? This person spends a big store in here. Now the immediate next person needs to wait long time. right? T is extremely larger because of this person. Sometimes all these people finish their transactions, but this person is waiting for this transaction. That's theoretically really disadvantage. Do you agree with me, guys? The story is extremely disadvantage of this. But we are working with psychologists. We are different people. Assume we have four counters we have. Each counter consists five people, right? Five people. So the queue is shorter, isn't it? Queue is short. I have only five people, right? I have five people to get to the service provider or the head or the cashier. But in this story, guys, we can see, oh my God, 20 people in here in front of me. People would not realize the speed of the service, isn't it? So, because we are working with normal humans, right? Normal people, not the super excellent, innocent, and very nice and gentle people. So, it's a big story. So, you should understand. Whether we are highly technical people, we have much more complicated things too behind the scene. That's why I want to open this eye, unless you might come up with a nice scientific approach. Yes, of course, agreed. But you may apply all of these scientific big stories definitely to computer systems and so on and so forth. But if you are dealing with a human, please aware with these things too, because you are working with a human. So if you are applying Kevin theory, please be careful whether you are working with completely a system or with humans too. If it is just system, no worries at all. You apply it as it is because they are happy, right? If it is with human, please be careful. We have another factor, that is the human psychology, and different kinds of human factors. We have feelings and all of these things. Let's discuss steps in capacity planning. First of all, we need to assess the current capacity so we can understand the existing production capabilities and the constraints. We have to find the capacity, what we can do now, right? What we can do. Then we can forecast future demand, use the forecast methods to predict the future demand. Let me give an example, then you can understand it easier than ever. Now, for an example, we have set of lecturers in our department. Like for an example, we think 10 people we have, 10 lecturers we have, and we have a lot of lab assistants. We have temporary staff like probation lecturers, like kind of people. We'll take all the senior people. We have 10 people in this organization. These people are the decision makers. These people are taking this university into the right direction, right? So this is the current assessment. For these 10 people, we will assume we have 500 students are working under these 10 senior lecturers. Under these 10 senior lecturers, there might be a lot of temporary probationary lecturers might be there, temporary staff might be there, and so on and so forth. I'm not coming to that layer. I'm speaking in a very high level layer. Now university is taking, or this department is taking a decision, will increase the number of students into 1,000, right? Now, at a glance, your answer is yes, of course, we have to go for 20 senior lecturers, right? Right, then definitely your simplest approach. If I ask this question, what is your answer? I don't have time, guys, to be like interactively discuss all of these things, because we have only 2 hours. So within 2 hours I want to deliver all of these things, unless this is a nice discussion, to be honest, for you too, right? The simplest approach is, if it is doubled from this thing, this is x, so this is 2x, right? This is 2x. If it is an equation is, right, x is y, so 2x is 2y, right? In simplest mathematical equation. Definitely, so we need to have 20 senior lecturers, which is a big problem. Now let us see how to tackle that story. Now we have to identify the capacity gaps. Compare the current capacity with the future demand to find discrepancies. What kind of things that we can find? For an example, among these 10 senior lecturers, there is only one English lecturer, right? English senior lecturer. And there's one management lecturer, whatever subjects that's teaching management related. Okay. So you can see, right? The rest of the 8 people, I'm getting very high level numbers, right? These are the technical lecturers or the senior lecturers who are delivering computer science related subjects. So at a glance, you can see we do not need these 2 English lecturers. The same lecturer could be able to tackle, because subject wise there's no much subject changes are going in English language. So if we have 500 or 1000 students, the number of papers are changing, number of assignments are changing, but the content or the subjects are not changing. So we don't want to hire another English lecturer. Same story for the management. Yes, of course, there's no subject or a content changing, so we don't want to hire another senior lecturer. We'll keep those 2 as it is. The rest of the 8 people almost doing the computer subject, and the new introduction subjects are there, right? So do we have some new introduction subjects? So at a glance, you can see not 20. Now you agreed, right? It's not 20, it's 18 is enough. Agreed? 18 for 1000 is enough. This is a simple example for you to understand the capacity gaps. Right? You should understand where the story is, where the story lies. Right? So you have to go in detail to perform this story. Oh yeah, we don't want 20. If we analyze a bit more the subject wise, we can find, yes, of course, 18 is enough. 19 and 20 English and management lecturers, well, they can continue this stuff as it is. Yes, of course, you can have a single constraint. You can simply say, yes, of course, we want some additional tutors or the marking assess, marking examinations and so forth, because the number of students are increased. But the salary wise, they are getting a lot lesser than a senior lecturer. So it's manageable, right? Rather than hiring 2 new senior lecturers, we can hire 4 new marking examinations. Simple, right? So we save the cost. Yes, of course, it's a capacity gap that we have, then we can tackle, right? We can have, there are 3 academic coordinators we have, right? Then what my suggestion is, we'll take 1 academic coordinator for the academic coordination and these 2 for the non-academic coordination. Yes, of course, we can do, but again, please be careful. We are working with human. If something gone wrong, they are getting upset, right? They escalate, they many things. So be careful, right? Whatever things that you, if it is a computer, yes, of course, this is the best approach, but we are working with human, even though those are people like lecturers and academic coordinators. Well, next, develop alternatives. Create plans for the increasing capacity, such as new equipment or the shifts. Yes, of course, the same story that I'm telling. Here we have a strategy. We'll take 1 coordinator out and let these 2 people to have this non-academic work and this academic coordinator to that front. Or else we can have, like, we don't want these additional 4 marking examiners. What we can do, we can develop a system, a computer system which tracks your TMS and stuff. It's marking automatically. Well, it's a nice story, right? We have an alternative. That alternative is giving a nice story, nice gap. It helps a lot for us to manage our time and the resources. Understood? Yeah. Yes. Next, we'll go to the next point. The next point is evaluate alternatives. Assess the feasibility cost, benefits each alternative. Now we have to evaluate the alternatives. Now the problem is we are increasing the size of the people, and I have 2 alternatives suggested. The very first suggested alternative is having 4 marking examiners instead of 2 senior lecturers, right? And the other alternative we have is automated marking assessment tool. Well, now we have to find what is the cost and the benefits of the alternatives. The time that taken, the cost is not the monetary value that we are speaking, the efficiency and all of these things related to. If it is automated or computerized machine or computerized marking, most probably within a couple of minutes, sometimes seconds, or in real time, we can get the results. If it is if we are hiring additional 4 marking examiners, yes, of course, it's a big story that we need to focus, because we have to call them, we have to seek them, we have to find them, we have to advertise, right? We have to do lot of things, and additionally, we have some papers like pens, all these cost. The traveling cost for them, if it is they are working from home, uh, it's a big story that you should understand. So now we have to evaluate what are the alternatives. I have given only 2 alternatives. There might be many alternatives we have. Then we have to go for a cost benefit analysis or any other methodology that fits for that scenario. Then we have to find the alternatives we have. Next, what we are going to do is we are going to implement what is the best solution that we found. For an example, we are spending some large initial amount to automate this marking process. TMA markings are doing by automated. So we are developing a software. It takes cost initially, yes, of course, because software engineers are expensive people, yes, of course. Then later on, it's nothing like, it's just maintaining. So we agreed. So we are implementing the plan. Yes, of course, it's fine. Let's monitor and adjust. Now we have to monitor and adjust the system that we have implemented, right? We have to find the accuracy, whether we are doing all the markings perfectly. Is there any gaps we have, any missings, any issues, any bugs? In case the first proposed methodology is insufficient or it's not working properly, we have to go for the alternative again, right? We have to come and see, and back and forth we have to do this evaluation, different kinds of alternatives, because first alternative is not working, though we selected as the best approach. Next, what we have to do is we have to focus on hiring some of marking examiners. Yes, of course, we'll hire these people, and we'll see whether they are working or not. Again, they are not working at all. It's a big mess. And we have to call them, we have to find them. Where are these people? They are not coming, they are not, we don't know anything. So it's a big story. We have to go for another alternative and so on. After a couple of iterations, we'll find the most optimal methodology. After a couple of iterations, sometimes the very first, if we find the best methodology the very first time, we are really lucky, so we can continue the work. In case if it is not, still we have some scientific approaches to find the best alternative. Somehow we have to implement it. So I believe you got the whole story of this capacity planning, how to handle this capacity planning properly, what kind of things that you have to do. Simply, guys, to be honest, it's not just for an organization and so on and so forth. Even in your personal life, you might find a lot of capacity related issues. For an example, managing your time, right? Managing your time. You have, sometimes you are married, you have babies, right? Sometimes you are working in one organization and you are doing some part-time job in another organization, right? You have to look after your parents. Sometimes there might be some additional people that you need to look after, like for an example, your aunts, uncles, or some older people, your grandfathers and stuff, right? So you need to take your babies to the school, and all of these things you have. Your capacity is insufficient. So you should plan, especially you have one kid, very soon you have another kid. Now you should plan your future. These are practical scenarios. These are very practical. I don't want to like tell all these big theory and stuff, because you are in a practical level. If it is A levels, yes, of course, that's like bit of theory. Now you should get the hands-on experience. You should do it well. Then you can understand. Software engineering, wherever you might be a project manager, you should plan capacity plan properly. If you are a cloud engineer, especially, I'm pretty sure there's a cloud person called cloud architect who is really bothered with this plan, because he needs to give a forecasted plan for next month and so on and so forth, right? So we have to adjust. Organizations wise, we have to handle it properly, and a nice story that you have to do. Why this capacity planning is important? Yes, of course, now you have some understanding. It's cost effective, right? The best method always cost effective. Cost effective means even for a pen and a pencil, or even a 5 minutes or a 1 minute is effective for us, because we want to save our time. We want to save our all of these things, right? Give me a second, guys. Right, sorry for the disturbance, guys. It's cost effective, right? It's not cost, it's not just the monetary value, it's the time. Time is the biggest store that you should manage. Now you should can understand it nicely, and customers are satisfied if we are giving our work with a minimal time. We are happy, right? Think, assume, some of banks, if you go to the bank, it takes hours to hours to hours to get a work done. Especially, like, I'm sorry to say, if we take many university work or many government work also, it takes hours, months, days to do a task. People are unsatisfied. People are unsatisfied. That's the story, right? People don't like, oh my god, it's taking hours and hours. People want to get the work done quickly because they have a problem. They want to solve the problem all of a sudden. But the people, some of the, like, I don't know, I'm sorry to say like this, some of government people are telling, why not they have planned it properly? It's really hard to plan, right? It's really hard to plan many things. So they should understand it clearly. They should focus on, all right, this is a customer that we should focus. In my point of view, because students are the best customers for myself. So I'm always happy to help them, because if you are happy, I'm happy definitely, right? Though this is not a business, right? Though this is not a business, this is an education story. My customers are happy, my students are happy. I'm really happy for them. So we need to increase the capacities in different kinds of places. Next, competitive advantage. We can get a big competitive advantage by proper capacity planning. If we have to target this much of, then we can have this kind of resources, and we can increase the number of students in our campus. We can increase the number of lecturers or anything that we want, and we can compete all the universities, because the largest number of students we have, right, rather than the other places. So it's a big story, and we have a good educated lecture panels, right? All of these things we have. So if we plan it properly, now we can go for a nice competitive advantage easily. Then the risk management. Actually, the risk is nicely managed, because we know what happens in future. The biggest problem is, like, even if you join to an organization or somewhere, all right, we'll manage it, right? We'll manage it. That's fine. That's not the story. There should be a proper plan. People initially would definitely distract with this planning. They don't have much experience, especially the people who do not work in industry and come into these mm, public government places, organizations like universities. People do not have much private sector experience, right? So they let the risk as it is. They flawed the risk. So it's a big story, guys, to be honest, right? Because we don't know what happens, where is happening, how it's happening, and so on and so forth. It's a big disadvantage. If we properly plan, the risk is minimal. That's why we are having all of these risk management, risk contingency plans, and so on and so forth. Probably you might learn all of these things under project management, but I just keep it for you now. Next, what are the challenges in capacity planning? Demand uncertainty, right? Definitely, we have some uncertain demands. We have technological challenges, right? We might see this kind of software is the best software, but later on we realize that is not properly connecting with the database. Oh my God, it's problem, right? Because if you don't have a person with superb experience, or we have some superb software or something, we might have these software like technological challenges. Financial constraints. Next, we have different kinds of financial constraints, especially the some of markets are changing, right? Some of the things changing in many times. Sorry, right? Markets are changing, and sometimes the country wise, for example, what happens to Sri Lankans, right? All of a sudden the vehicles are gone. So the financial constraints are changing. Supply chains, right? It's supply chains varying means interruption for the entire story is changing. If any case, if you find any supply change is interrupted, everything is changing. I'll give a very simple example. If no fuel to Sri Lankans, or no fuel for buses and lorries and cars and bikes and all of these places, what happens to us? I think you have this experience, right? Supply chain was broken. Even everyone suffered from that. Every Sri Lankan suffered from this supply chain interruption. So we have to keep the supply chains nicely, because it's really important to an organization. In case if there's a supply chain is interrupted, it's a big challenge for the capacity planning, because we assumed this much of fuel or the oil might be in our organization this time. Due to different kinds of political, economical, or any other issue, these chains are breaking. It's a big story that you should understand. It's a big impact at the end of the day, right? Again, we'll discuss what is the performance. Sorry, it's not introduction. It should be like performance analysis. Uh, the summary of this story, right? It's a big story that we have understand. We have different kinds of evaluations, different kinds of business sectors we have, right? We have lot of things at the end of the day that we have to deal with this capacity plan, right? um, Summary, I'll change it, summary. Right, any questions, guys? I can give quick second for questions. All good. Right. Next, we'll discuss probability. Probably you have learned, right? Probability in grade 6, 7, 8, 9, 10, or until A levels, or even your undergraduate time. You have learned this probability very well. You you know the probability very well. Occurrences. So it's a quick brush up for you, right? It's a fundamental concept in mathematics and statistics, basically, to check the likelihood. Yeah, what will be happen, right? We can't specifically tell 100 out of 100 means there's no probability. It's a must. Zero means nothing. There's no possibility to having this kind of a scenario. I'll give a very simple example. There's no probability that sun rises from west, right? And we have 100 out of 100 surely, or guaranteed probability that sun rises from east. So that's the story of this probability. In between, there are many things that we can't specifically fix. There might be a rain or not based on different XYZ facts. We can tell 0.7 probability that today there will be a rain. So that means high probability. 0.9, very high probability. 0.3, low probability. 0.2 or 0.1, very low probability that there could be a rain. So I believe you understood all of these things. To understand this probability, you should have some key words in your head: sample space, events, and the probability of an event. Sample space means a set of all possible outcomes of an experiment, right? Then event is a subset of sample space. That means the sample space that we have taken represent the specific outcomes of or combination of outcomes, right? It's an event basically. Then probability of an event, when this event can be happen, a number between 0 and 1. As I told you, a number a value in between 0 and 1 that indicates the likelihoodness of the event that occurring. There 0 means impossible, 1 means definitely certain. I have given examples to understand this probability of an event. I believe you understood this sample space, and I believe you learned all of these things, but just a quick recap for you. Different kinds of probabilities we have: classical probabilities, empirical probabilities, subjective probabilities, and so on and so forth. Right? Classical probability is something that you mostly use based on the like of outcomes. For an example, rolling a fair six-side die has classical probability of 1/6 of each face. Right? So we know if we either say we will take another example. If it toss a coin, so the probability is one, right? So that's the story that we have to understand. Next, empirical probabilities. It's based on the observations. There's no specific numerical values. There's no hard and fast truths, right? So what we have to do is we have to check, oh my God, Sri Lanka will win this cricket match. There's probability of this much and that. But yes, of course, right? Computers are generating all of these things. Sri Lankas are changing, right? These empirical probabilities many times it's changing, right? People are telling whatever things might be incorrect in many times. Even the software systems based on some of data, still it's not well worked. So there might be some probability things. Subjective probability based on personal judgments of beliefs. Right? It's often when the objective data is unavailable or insufficient. So this we don't have sufficient data, right? We don't know what happens next. So it's just a subjective. We just think, right? For an example, I found a person in an interview. So I don't. This is the very first time I'm going for an interview, right? To interview a person. So that person is telling myself and all of these things. Yes, of course, we are happy with that. Then we hire. Because we don't have data, but that person is not performing very well at all. It's a big story. So it's a big point that we should understand with these subjective and empirical probabilities. If we have scientific approaches like classical probability, what you have did last couple of years, yes, of course, it's a big advantage for you. Some of probability rules that you have learned. What kind of probability rules that you have learned? Yeah, probably you have learned all of these things. Additional rule, multiplication rule, complement rule, and so on and so forth. I believe I don't want to give these examples again and again, right? So you can continue the word. What is this conditional probability? Conditional probability means a situation, an event occurring given that there is another event already occurred. After a specific event occurring, the next event is occurring, right? So they are like the first event occurs, then the second event is occurring. So that kind of a scenario that we are focusing on, right? So after first event occurs, the second event is occurring. How much is the probability? So this conditional probability is something very interesting. Sometimes it hurts us a lot, right? So some of the math questions that focused under this is a bit complicated it sometimes. Yes, of course, I agree with that. So somehow I believe you learn your O levels or A levels. Independence and the dependence, you should understand the independence and the dependence very well. Events A and B are independent if the occurrence of one does not affect other occurrence of another one, right? The other one is event A and B are dependent if the occurrences one affects the other occurrence of another one. For an example, if we take a bag of balls, then if we take a random one, right? There's no depend with the other one, right? Other ball, right? So it's kind of a scenario that you can understand. Random variables and probability distributions. Now we have random variables assigned to numerical values outcomes of a random experiment. Random experiment means at the beginning we don't know the mathematical equation. Some of if you are like if you are like player of these cards, probably all boys, right? Sometimes girls too, right? So you might play this deck of cards, and there are mathematical games too, guys. I don't know whether you learn all of these things. Go to YouTube and play some mathematical games we have. Right after shuffling, we can have 8 cards out, second card on top, then the last 7 card is the same card that we have taken, kind of like an example, right? I don't know, right? Even I experimented, it's nicely working, guys. Right? It's a nice scenario. Even I can't believe what happens. It's not, we believe, right? It's a random distribution in this case, but it's not random. If we take into mathematics, yes, of course, it's automatically coming. I don't know how, right? It's a nice story behind these things. The mathematicians should find this story very well. That's what I'm telling is random means we have no data, right? We don't have algorithms and so on and so forth. Next, a probability distribution describes the likelihood of each value of a random variable, right? The other one is common probability. Distributions including uniform, binomial, normal, or the Gaussian distribution and exponential distributions and so on and so forth. Today, we are learning a bit of these things too. I'm not going to in detail, but I'm planning to have a couple of tutorials to be recorded and upload most probably. I can't give a guarantee, guys. If time permits from my end or someone from mathematics, I'll take one lecturer, right? And I'll try to create at least one single what we call video to discuss all of these things to do, right? So the next one is expected value and the variance. The expected value or the mean of the random variable is the weight average of all possible values weighted by their probabilities. Now, these weighted values are very important, right? It's very important, right? So what we have to do is we have to handle these values, right? We have to handle all of these things properly. Variance measures means spread or the dispersion of the probability distributions around its mean. Now, expected value and variance giving a nice overview for you to understand how all of these things are floating the data sets, especially once it comes to data sciences and other stuff, how the data, like, I don't know how many of you are learning data science. In that case, we have exploited data analytics. We are exploring the data set, how this variance is going throughout the data set, right? How the data set is going throughout, how this data set is focused on, and so on and so forth, right? Any questions, guys, up to now? Quickly, 1 or 2, 5 seconds probably. No questions? Okay, then we'll continue to the next one. Law of large numbers and central limit theory. The law of large numbers states that as a number of trials increases, the sample mean approaches the expected value, right? So that's the simpler theory that you have learned up to now. The central limit theorem states that the sampling distribution of the sample mean approach the normal distribution, right? So what we are telling is the sampling distribution of the sample mean, right? The sampling distribution of the sample mean approaches a normal distribution. That means it's distributing throughout the proper alignment or alignment. Then we have to, as the sample size increases, regardless of the shape of the population distribution. So it's a big story that we have to understand. We have to focus on that things very well, right? So we have to focus on that, and we have to find how to handle all of these things nicely. What are these stochastic processes? Now, stochastic processes are again a different story than a mathematics. It's under this mathematics umbrella, but it's not the same as probability, right? So probability I haven't focused a lot because I believe you are much familiar with these things. Somehow we'll try to understand what is these stochastic processes are. Stochastic processes are mathematical models, again, I'm telling, right, used to describe the evolution of random phenomena over the time or the space, right? These processes are essential for understanding and analyzing systems that exhibits randomness or the uncertainty. Now, I believe you are not much familiar with these kinds of stochastic processes. So I'll spend bit of time with you to understand, right? To understand a bit of these things, right? All right. There's a question related to exam. We'll discuss it later on, right? We'll discuss it later on. But actually, a quick answer is most like what you learn is evaluating in the examination, right? You don't get any question out of these things, though last time we had this kind of thing. Yeah, that's fine. We'll discuss it later on, guys. Somehow, I want to tell you in a very high level, right? What we need to do, right? What kind of thing that we need to focus on, right? What kind of thing that we need to do for the examination? I don't think so. Like you need to do a lot because all the theories are discussed. Whatever things that we are discussing today will be minimally evaluated this time compared to the last. I believe it covers some of the things that I want to tell you. But somehow, if we like, if time permits, definitely we go for a much detailed discussion. What will happen for that? Somehow, again, we'll back to our discussion, right? We'll see this. What is this stochastic processes are, right? Once it comes to these stochastic processes, these are the fundamental tools in various fields, including mathematics, statistics, and many other things. These are used to model random phenomena like the story that I told. Imagine a person standing at a point on a straight line, right? Each time step, this person randomly decided to take a step neither left or right. with equal probability, right? This person is given a chance, okay, you can go for left or right. We are not telling, we have only two options. This person can go left or right. This is a simple example of stochastic process, right? It's known as one-dimensional random walk, right? So sometimes you heard these random walks and stuff. Don't worry, I'm not messing you up, but I'm just want to explain a bit of these things. Now, how to tackle this story, right? How to uh, work with this discussion. Initial position, right? We have to understand where the person starts at a specific point on a line. We'll get an example that's the position is 0. Right? Random movements. What kind of movements that the person is going to have? Each time step, right? Each time stamp in every time, the person randomly decides, right, whether to move one until the left or right or whatever the places that we want. Then it's repeating again each and every time stamp. So this position of the person after a certain number of steps represents the evaluation of the random processes. Right? Now we'll get this random scenario again, starting with the zeroth at the line. Then we have random movements. We will get some random scenarios in the very first like very first second or very first minute, some whatever things. The person randomly moves until to the right, end up to the position 1. Then it goes to in the next time slot, randomly move until to the left, ending up back to the position 0. Again, move until to the right, again to the 1, right? I believe you learn all of these things and somewhere, right? It's just the movements of this left and right. So it repeats this process. Right? So these stochastic processes like random works are not uh, only useful for the modeling these movements and stuff, but in everywhere we can use these scenarios, right? There are a lot of frameworks and so on and so forth to get clear understanding what are these things. I believe this example helps you a lot. Sometimes it may stop you a lot. Don't worry, you can go for some additional references and definitely you can learn. Somehow it's just supportive for you. I don't know whether uh, this quick uh, this quick example might problematic for you, but don't worry, I'm really sorry if it is problematic for you, because if I want to explain this story nicely, it takes at least 10 to 15 minutes, right, to go through all of this stochastic process and how this random walk happens with an example and like drawings and stuff, but it's really hard. Right, next we'll go for these story to handling these scenarios. This is a simple definition. A stochastic process is a collection of random variable indexed by the time or the space. It represents the evaluation of a system. The randomness is playing a significant role. We don't know, it's a very high probability of a very high story of this randomness. It's really hard to tell. Somehow again in that scenario we have another set of things, right? We have some additional steps. We have sample space, index set, and we have probability distribution, right? What happens in these scenarios, right? What happens in these scenarios? We have a set of all possible outcomes for each random variable at each time or spatial point, right? Now we have a lot to understand with this sample space. That's not we have this sample space of all possible outcomes, right? All possible. Some of random variables is really hard to grasp all of these random spaces once it comes to this practical scenario. it's really hard to grasp all of these things. But later on, we can see, oh, we can have this kind of XYZ facts, and we can have this kind of a scenario, and so on and so forth, right? Then the index set, uh, the set that indexes the random variables, right? Typically representing the time, or what we call this discrete or continuous, or the space, right? It might be one dimensional or it might be multi-dimensional. Further, we have probability distributions. Probability distributions describe the how it's associated with the probability outcomes of the random variables at a different point in a time or a space. It's a big story for you now, but if you go through, it's not a big story. Don't get upset, right? Types of stochastic processes. We have different kinds of types in these stochastic processes: discrete times stochastic processes, continuous Markov processes, Markov chains, Brownian motions, right? Lot of things we have, right? We'll get some understand in this scenario, right? We have random variables are indexed by discrete time points, right? Discrete time stochastic processes, right? Discrete time processes are telling this kind of a scenario. Then we have continuous time stochastic processes. Random variables are indexed by a continuous parameter such as time. Right now, continuous time stochastic processes, the random variables are indexed by a continuous parameter. Now, once it comes to these discrete time stochastic processes and the continuous time stochastic processes, you can see we have a continuous or a discrete points in our data set, right? Or the evaluation metrics that we are using. Even if we have continuous days, right? For an example, for first, second, third, fourth, and until 30th day, we can have sometimes the continuous time stochastic process to be applied. Even if it is seconds, right? Even if it is seconds, if we have uh, a symmetric distribution of these points, then we might find some of interchanges in between these discrete and the continuous processes, right? Then we have Markov processes, right? What are these Markov processes? Right. So I believe you got clear understanding what kind of types of stochastic processes we have to uh, definitely go through. Actually, we'll see to, I'll try to give some additional references for you to understand. To be honest, guys, if you want to understand Markov processes, it takes a lot of time, right? Within 5 minutes you can't understand. There might be some superheroes, I don't know, there might be, yes, of course. For me, it takes hours to understand what happens in these Markov chains and all of these things, right? So I'm really sorry if someone is hurt. For me it takes hours. So I'll give some additional resources like to you to understand what you need to go through and so on and so forth. We'll see, right? I'll try to give my level best to get much more understanding in these contexts. What kind of properties we have? We have stationary independence, and what happens in this stationary, right? Uh, Stationary, the statistical properties of processes remain constant over time, right? So what we are going to do is the statistical properties of the process remain constant, like whether the time changes, all the statistical processes are keeping as it is, right? Or are time invariant on average, which is known as weak stationary, right? In case this time invariant, right, invariant on average, because it's not constant, then we can find weak stationary. That's one of biggest property that we want to satisfy in this scenario. Then the independence, random variables at different time points or spatial locations are independent. Independent increments we have, right? Then we have erodicity. The long-term behavior of the process can be inferred from single realization, right? So these are properties that we need to satisfy, right? So that's a big point. That's a big thing that you should do. It's a must, right? It's a must to understand these things very well, right? Um, where's my screen? Right. Fundamentals of the queuing theory. Now, we learned the story of this performance, and we understood the probability, and we understood the stochastic processes, right? But a combination of all of these things, can represent in this queuing theory. What happened in this queuing theory? Queuing theory is a branch of mathematics and operations research that studies the behavior of varying lines queues in a system where the entities such as customers, tasks, or packets of data arrive at a service facility, wait for a service, and then depart. So the simple example that you can understand, when you are a bank, I mean, ATM queue at least, uh, in a bus queue or many places, not in a train in Sri Lanka, right? Not in a train in Sri Lanka. Definitely, buses, even we have these interruptions, many places, but in some places we can find in banks and stuff. This story applies for many fields. Lot of fields we can find in many places. Components of a queuing systems. We have an arrival process, we have servicing processes, we have queuing discipline, we have queue capacity, and we have a queue length, right? So these constraints are really important, or the components are really important, because it gives a clue of where to apply and how to apply and all of these things, right? So it's a big discussion at the end of the day for you to understand how these things are working and so on and so forth, right? What are the key performance measurements we have? One is utilization. The fraction of time servers are busy. That means we have all the agents are busy. Average queue length, expected number of entities waiting in the queue, right? Number of people. Average waiting time, expected time entities spent waiting in the queue. Throughput, the rate at which entities are served by the system. Service level measures the performance related to the waiting times or queue lengths, often defined as probability that an entity who waits lesser than certain threshold. Right. Well, um, I don't know whether you have learned operating systems or not. Once it comes to this operating system, we are learning a similar scenario. Can you remember, guys? We have process model, right? Sorry, the execution model, right? The execution model. We have all these tasks are starting and running, right? Can you remember this scenario? This is some waiting, and we have some services in here. It's dispatches, right? And it did, right? Every process, right? We have this very high level scenario, and at that time also you have probably calculated the average waiting time, throughput, and so on and so forth. Probably you have learned the same scenario applied in this case. There's nothing, no difference at all, right? If you learn it properly, so there's no much differences at all, right? But some kind of common models. Now this queuing theory is very powerful. That now you understood, right? Already you have good understanding the importance of this story. What are the common models that we have? One is multi-server queues. I'm going to discuss this one a bit more detailed today. A basic single server queue with a Poisson arrivals and exponential service times. Again, I'm going to discuss what is this Poisson distribution a bit, like a recap, right? To be honest, it's a recap. And I'm going to discuss exponential service times too. Then we have MMC queues, an extension of MM1 queue with multiple servers. The same story, extra expanded to multiple queues. Then we have MG1 queue, a queue with Poisson arrivals, general service times, exponential or otherwise, and single server. MD1 queue, a queue with a Poisson arrivals, deterministic service times, and the single server. So at a glance, it might be really hard for you to grasp, guys. I'm pretty sure. Yes, of course, agreed with you. There's no arguments. At a glance, you can't understand, but after learning these things, some words might be in your head. Go through again all of these slides and stuff. I'll upload all of these slide decks to the course page as it is. Then you could be able to find much more details, go much more references, as much as then probably you can survive yourself easily in the examination. Don't worry, I'm not asking lot of questions in the examination in these contexts. This multi-server queues, an interesting point that we need to understand. Multi-server queues, known as MMC queues in queuing theory, are systems where multiple servers provide service to arriving customers or entities. These queues are an extension of the single server queue model and are particularly relevant in scenarios where a high volume of arrivals needs to be managed efficiently. So it's a big story, right? It's a big story that we should understand how to handle these extensions nicely. Right? Next, components of multi-server queues. What kind of components we have? Like nearly same scenarios we have. Arrival processes, right? Basically, these are following the Poisson distribution, right? With a mean arrival rate of lambda. Then we have service processes. Each provides services at the exponential rate, that is mu, right? We have some exponential rate. There are C servers. There are servers. There are C available at the service time in the arrival entities. We have the entities are coming high up exponentially growth. In that cases, with these service processes are doing a lot. Then queue discipline, commonly first in first out. I probably believe you learn this first in first out somehow. Whenever we have a queue, right? Whenever we have a queue, this is the queue. This is the person who entered. Then this person goes now easily. The second person comes, then person goes out. So there's no changes. For an example, time t equals to 0 starts in here. If time t takes to finish this queue, this person is alpha node, is node alpha, would definitely receive to the end where t equals to t, sorry, alpha will stay here in t equals, right, t equals, this alpha will stay again t equals to t. If it is the next node beta, right, beta arrivals to the same queue in the same time, right, that means t equals to 0. Since this one consumes this processes, right, if this serve time, this time that taken for this scenario is will take t1, right, then this beta node will ends the processes where t equals to t plus beta, sorry, t plus t1, right, t plus t1, because this, though it's arrival the same time, sorry, the t1 time, one small time difference we have, right, plus t2 will take t after t2 time. This task is coming, right, task is this beta is arriving in t2 time, right, the same time. So this is the time that takes to this queue discipline once it comes to this first in first out discipline. But we can't specifically tell that's only first in first out. We have priority queues, we have round robins and blah 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 things we have, right, lot of things we have. So these all of these things might fit for different kinds of scenarios to work with these things. Next, we'll discuss some of networks related to this scenario, the open networks and the closed networks. Open networks, also known as open queuing networks. Type of queuing model where entities or the customers, packets, jobs, whatever, enter the network from the outside, receive service at one or more nodes, then either leave the network or move another node for further service. This constraints with closed networks. This constraints with closed networks where the number of entities in the system remains constrained as it is. Open networks are widely used to model and analyze complex systems in telecommunications, computer networks, manufacturing processes, and service systems. Right, a lot of places we are using this open networks. So these open networks would definitely support you in many cases. What kind of solution techniques we have? We have analytical models, simulations, we have actual approximation methods. What kind of analytical methods we have? Using mathematical formulas to calculate performance measures for simple queuing models. Simulations, basically employing computer-based simulations to model complex queuing systems to estimate performance measurements. Now, once it comes to these computer scientists nowadays, we have a lot of opportunities open to for the simulations, because we want to see how these things are going, especially like traffic simulations, right? We have blood simulation. Uh, 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 so next one is approximation simulation or approximation methods. Using approximation techniques to estimate performance measures when analytical solutions are difficult to obtain. Now, approximation is that we are telling performance measurements when analytical solutions are difficult to obtain. Again, it's kind of a random zone that we are focusing on, and we are trying to grasp these things, right? These approximation methods are doing a lot for us in many cases to work in these scenarios. Somehow, I'll go to these analytical models, the models that we spoke, because simulations probably might take a bit of the work, and approximation methods are something that you can go through later on. I'll go through some of analytical methods in a general network. In more complex network, service times may follow general distributions. Inter-arrival times may not be Poisson. So even if it is and the networks require more advanced techniques such as network decomposition, analyze performance. So we should have a very clear and very general understanding with these analytical models, especially once it comes to this general networks. It's basically flowing through common inter-arrival times, not focused with these Poisson distributions. Next, we have Jackson networks. These Jackson networks are the special scenario of the same scenario. Right? We'll discuss with these Jackson networks a bit. A special class of open queuing networks where each node is a model as an MM1 queue or MMC queue. The arrival processes at each node follows Poisson distribution, and service times are exponentially distributed. The network has product from solution, meaning the joint probability distribution of the number of entities at each node can be expressed as the product of managerial distributions of the individual nodes. So these Jackson networks are very special scenario, right? It's a very special scenario when it comes to MM1 and MMC queues. I'm pretty sure now you are thinking, what is this MM1 and MMCQ, right? We learned it a couple of slides early, guys, right? I'm pretty sure now I missed a lot because it's almost 1.5 hours gone. So your brain is juggling here and there, but keep hang on, then you can learn from refer all of these things, right? Somehow we'll go to the next topic, which is closed network. Now we discussed what is this open network. We have closed networks. When the closed networks are closed queuing networks, or the closed networks that we are telling. These are systems where a fixed number of entities calculate within the network. Unlike open network, where entities can enter and leave. In a closed network, the number of entities remain constant. Keep in mind, guys. So it's very important to understand. In a not like an open network, right? Entities can enter and leave. In a network, in this network, number of entities remain constant. So it's a large door that you should understand. These models are particularly useful for studying systems where resources or tasks are recycled, such as manufacturing systems, computer systems, and transportation networks, and so on and so forth. Simply, closed networks are vital tools for modeling systems with a constant number of. These provides us valuable insights into the system performance, including throughput, utilization, and the response time. The product form solution, mean value analysis are powerful techniques to simplify the analysis of these networks. So you should understand it nicely, clearly, in a detail. So it's very, very important to understand how these things are performing and so on and so forth. Kind of key characteristics that you should understand. We have fixed number of entities, the total number of entities, the customers, and blah 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 things in the network is constant. We learned it. These entities move from node to node, receiving service at each node. Every node we are getting it. Then we have a service process. Each node in this network has one or more services providing service. Right? Service times at each node are typically exponentially distributed with a mean service rate where it's mu, right? The service rate is mu. It should be within brackets. After receiving a service at a node, entities move another node according to the predefined routing probabilities. It's predefined. This routing mechanism focuses, it follows a proper predefined routing probability. The movement of entities is usually determined by a Markov chain. So first of all, you should understand Markov chain, a detailed description in your head. Then you can understand these routing mechanisms easily. Finally, we have this network topology, We have different kinds of configurations, single loops, multiple loops. I believe you learn all of these things under network. So it's very easy. Single loops and multiple loops in the more complex interconnections we have. The structure of network impacts the performance and the behavior of a system and so on and so forth easily. What kind of analytical models that applicable in this scenario? We have product form solution, we have mean value analysis. Product form solution in many giving networks, particularly those that meet certain conditions. For an example, exponential service terms, Markov routines, and so on and so forth. The steady state distribution of number of entities at each node can be expressed as a product of individual node distributions. This property simplifies the analysis and calculation of performance matrices. So it's very important to understand this product form solution. So it's very common, right? Many close giving networks, right? We have this Markov routing and stuff. It's very common. So we have to find these steady state distributions of the number of entities that can easily affect, or we can take it down into these stories as a product of an individuals or the node distributions, right? The next point is the mean value analysis, a recursive algorithm used to compute performance matrices such as throughput, utilization, and average number of entities at each node. Mean value analysis is efficient and widely used for analyzing closed queuing networks. Again, mean value analysis is really important. Why it's happening? The recursive algorithm, right? Recursive algorithms, I believe you learned these recursive algorithms under this performance, algorithms subject. What is that? Algorithms and can't finish. Right. Data structures and algorithms, right? Yes. Right. Used to compute performance matrices such as throughput, utilization, and stuff. So it's very easy to calculate all of these things, right? I have a quick question for you to give a try. I don't give a lot of time. I have only 15 minutes remaining. I'll give maximum 2 minutes to give a try for you to understand what kind of thing that you are supposed to focus on, right? Quickly give me your answer. I'll give 2 minutes maximum. Right. You can chat. You can share the answer in the chat. You can chat with me. You can share your answer quickly. All right, I'll continue the discussion. Next, we have to discuss. In case if you write answer, please share it with me. I'm really happy to see your answers. Right, next we'll continue because we have very limited time. Come on, we'll come to these exponential and Poisson distributions. What are these exponential and Poisson distributions? Again, very important distribution types. Anyone, any ideas? What is this exponential distribution means quickly? Rather than one-way delivery. Shall we find any answer quickly? We don't have time again, guys. No idea. Nice, guys. So this exponential distribution shows a nice distribution story. How these things are like some set of data is distributed over time in common structure. You can see it is in the screen what kind of distribution structure we have, right? Next we have probability testing the density function. The probability density function is exponential distribution is given by this equation. Lambda is the rate parameter representing the average number of events per unit time. X is the time lapsed between the events. So in between these events, you might learn all of these things in a detailed way, definitely, how is these things are going through. We have a lot of properties to be satisfied. The exponential distribution is a continuous probability distribution defined for non-negative values of X. It is a one parameter distribution with the rate parameter lambda determining the shape and scale of the distribution. You can see it's a one parameter distribution, right? There's no multiple parameters going through. And the rate parameter that we define where is lambda, probably I should add this, right? Determine the shape and the scale of the distribution. The distribution is skewed to right, is of course, with a long tail extending towards larger values of x. The mean or the expected value of the exponential distribution 1 over the lambda is, and its variance is 1 over the lambda. We have a property called memory illnesses. So we'll discuss what is this memory illnesses. Probability of an event occurring in the next time interval does not depend on how much time has already elapsed. So it's a combination of a nice story, right? It's a probability of an event occurring in the next time interval means, right? Depend on the how much the time has already elapsed means. Mathematically, this property is expressed as this equation, right? Where x is the random variable following an exponential distribution and s and t are non-negative time values. So you should understand in a detail or a very important point that you should understand, guys. These random variables are following an exponential distribution. It's a nice story, definitely, right? And these are non-negative time values, definitely. The next point that I want to discuss is the Poisson distribution. Poisson distribution is again a nice right? Again, another distribution. There's a chat. Yes, I'll upload all these slides sooner I finished. I'll definitely upload these slides. All right. Yeah, we can. Yes. Yeah, obviously this is a bit complicated. Great to understand within a couple of time. It's a bit hard. So we'll continue. We'll continue because we have to complete it quickly. Then the next one is probability mass function. Again, we have this mass function is given by this equation. Representation of this k is the number of occurrences of the event, and non-negativity just simply lambda is the average rate or the mean of these occurrences within the given interval. E is the base of the natural logarithm that we are using. E, I believe you learned this E in many times. Again, we have set of properties. The Poisson distribution is defined for k equals to blah, 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 blah things. The mean expected value and the variance of the Poisson distribution are both equal to the lambda, right? So that's very important, the expected value and the variance of the Poisson distribution, right? The distribution is skewed to right, specifically for smaller values of lambda. As lambda increases, the distribution becomes more semantic and approaches a normal distribution. So you should clearly understand in a detail, you should understand how these things are working and so on and so forth. We have Poisson process. This Poisson distribution is often associated with the Poisson process, which is a sophisticated process where event logs, right? Now, again, I'm telling this event logs uh, with these things that yes, quick question, answered it. Personal question. Okay. Answered it. So let's see the Poisson processes, the time consecutive events of the process follows exponential and so on and so forth. We have this Poisson approximation. What is this approximation happens? This Poisson distribution can be used as approximation to the binomial distribution. The number of trials n is large and the probability of success P is smaller such that lambda NP remains constrained, right? So what happens in this scenario, the Poisson distribution can use, right, in this context, approximation to the binomial distribution, right? What kind of distribution we have when the number of trials in is larger? We have lot of larger responsibilities. Then we have a success P, right? Such that lambda equals to NP remains as the constraint as it is. It's not changing, right? We have multi-class networks. Again, a quick story coming to another subsection. Multi-class networks provide a comprehensive framework for modeling, analyzing, and many things. We should understand what kind of characteristics we have under these multi-class networks. It's not a single class network, it's multi-class network. So it's we have extended mean value analysis and analytical models too. In this case, last time we learned mean value analysis. Now we have extended mean value analysis and some of other things too, right? Again, same story, we have like similar to the single class. And finally we have product form solutions under these multi-class networks. We have to deliver, we have to understand what kind of things under this context of these products, individual nodes and the distributions are particularly when certain conditions are met. So it's doing a lot for us with these things. All right, any questions? Biggest thing, of course, there are thousands of millions of questions in your head. Number two, I don't know what to ask, right? Both ends might you have one of end, right? Probably if it's the very first time that you are learning all of these like distributions and stuff, but I believe you learn these things in somewhere in what you call what you call this mathematics foundation. Probably you have learned all of these things, but sometimes you haven't learned. This is a nice place to learn. Don't worry, all together bit of theory and bit of work there. Definitely go through again. Dr. Verika uploaded some of these things, right? Some of these things in the course page. So you can, like, I believe you have gone through almost, pretty sure a lot you have gone through. And I believe you understood almost things. So this is a nice recap for you in that case. So you might have some questions or not. Later on, even you can contact me, drop an email. I'm happy to help you. Last but not least, the questions. Yeah, again, mathematical actions, analysis, and the probability related stuff might be in the exam paper. Couple of questions might be there, not a lot, right? That the past paper that we have is like nearly focus on everything, most focus on just queuing theory. So I don't think so this time we need to focus a lot with this queuing theory. We'll much focus with the other stuff, because we have only 1/4 of the theory covered under this context. So for the most part, Mr. Nadir's part will be questioned in the final exam too. So you should prepare for that very well. Any other questions? All right, all good. No more questions. Okay, then, guys. If you do have any questions, even later on, let me know. Please drop an email. Please don't drop everywhere here and there, right, to different XYZ people. Just directly drop it to me. Then I will definitely respond to you, or else I'll redirect to the relevant person by sending to XYZ people. It might take some times going here and there and coming to me. Sometimes it's deleted, right? I don't know what happens. Uh, so if you want an answer, the simplest thing is directly drop it to me. Then I will redirect to the relevant person, or else if I can answer the question, definitely I'll reply for you. All right, that's all for today. And good luck for the examination and stuff. Do it very well. Probably you'll do something the best in your life for this subject. Okay, then good luck. See you. Bye bye. We'll meet soon. Thank you. Bye bye.